do the introduction. So today, we're very nice to have Professor Xiaoming Huo. So Professor Huo is a Russell Chandler III professor at the Sturt School of Industrial and Systems Engineering at Georgia Institute of Technology. Dr. Huo received a PhD degree in statistics from Stanford University in 1999. After that, he joined the School of Industrial and Systems Engineering at Georgia Tech, where he advanced through the ranks and became a chair professor. So from 2013 to 2015, he was a program director at NSF, managing data science-related programs. He's the director of the Transdisciplinary Research Institute for Advancing Data Science at Georgia Tech. He's also a fellow of ASA. Dr. Huo's research interests include statistics and data science in general. He has made numerous contributions on topics such as sparse representation, wavelengths, and statistical decodability. His papers appeared in top journals, and many of them are highly cited. So the title of his talk today will be on a homotopic method to solve the lasso problems with an improved upper bound of a convergence rate. So without further ado, please join me and welcome Dr. Huo to give the presentation. Thank you.
Yeah, thank you, Lily, and thanks for inviting me here, and thanks everybody for being here today. I guess let me first figure out how to share my screen. I'm going to assume that everybody can hear me.
Yes.
And yeah, just click the share screen button. But I don't see. Oh, I think somebody. I saw that the host disabled participant screen sharing, so I cannot share my screen. Do I have to log in and log back in again as a host?
No, would you like to try again? Maybe.
Okay. Okay, now I can share. Let me share my screen. Just give me a second. And I'll go full screen. So I'm going to, I think I'm going to assume that the screen sharing is working properly now. And
yes,
everybody can see the title screen. Great.
Yep. Yep.
So I'm going to talk about a homotopic method to solve the lasso problems. And in particular, I would mention the main contribution is that we can prove a better upper bound in terms of the convergence. So my name is Xiaoming Huo. I'm a professor in the Georgia Institute of Technology, and this is a joint work with a PhD student, Yujie Zhao, who is jointly advised by me and my colleague Yajun Mei. And this is the agenda of the talk. I'm going to start with the motivation, introducing why are we interested in this type of the problem and which kind of result we are going to get. And in the second part, I'm going to talk about some benchmark methods, which are considered the state-of-art algorithm to solve the problem. And we're going to explain which kind of improvement we can make over those benchmarks. And in the third part, I will dive into the details of our particular algorithm. And in particular, I'll talk about the homotopic approach that we've taken. And we are going to, in the section 4, talk about some theory that we can derive based on these methods. And follow that, I'll talk about the numerical experiments to validate the theories. And finally, I'll give some concluding marks. So let me start with the introduction part. And this work is motivated by the Lasso algorithm. And I'm going to assume that everybody have heard about at least this terminology called Lasso. And obviously, this is a method which has made a tremendous impact in the past 2 decades in statistics, computing, data science, and many more. And there's a huge amount of efforts inputted into it, and a lot of theory has been developed. So for example, the theory associated with the lasso to proving the exact recovery of the support sets, the minimax estimation of minimax rate in the parameter estimation, those probably becomes nowadays the standard teaching materials that we do in the graduate school in the first year PhD in statistics. And also it has a tremendous impact in the application because, for example, a lot of biostatistics related applications, if you zoom into the algorithm they apply, most likely the lasso is one of the algorithms that they use at least as a benchmark. So tremendous impact on these methods. Now, what is a lasso algorithm or the idea of a lasso? Let me start with first introducing the data generation mechanism that we are going to assume in this talk, and this is going to be the foundation of some of the development that I'm going to talk about later on. So we are going to stick with the traditional linear regression setting, and the equation you saw in the middle of the slides is a typical way that we describe the linear regression problem. Here, the left-hand side, y is what we call the response vector, which is a vector of the value that you observe for the response variable. And x is what we call a model matrix. So for the matrix X, each column is associated with a predictor or covariates, each row corresponding to our observation. And beta star is what we call the coefficients vector. And I add a superscript star there. This is the traditional way in statistical literature to indicate that this is a ground truth. So you always assume that there exists a ground truth, but nobody knows what the ground truth is. And the job of the statistician is to try to uncover this ground truth as much as possible. And this the last term on the right-hand side, the W is the noise vector. And noise vector means that each element is a random noise. It may be follow some normal distribution or some sub-Gaussian distribution, and so on. So now, the objective of statistics is to try to uncover the ground truth or the underlying model. So this underlying model, it could be the beta star, which is on the previous data generation mechanism. Sometimes it is about the inference result, which is x times beta star. So both have their corresponding criteria in terms of the model estimation in the statistical literature. So the Lasso estimator, what it does is that it is essentially solve a minimization problem, which is you can see that in the objective function, it is made of two terms. And the first one, which is y minus x beta, and then you calculate the sum of the square of this vector. This y minus x beta vector is essentially the vector of the residuals. And if you calculate the square of the L2 norm, that is the residual sum of the square. So the first term in this objective function is basically the goodness of fit of the model. And the second term, which is lambda times L1 norm of beta, the L1 norm of beta by definition is the sum of epsilon values of the beta vector. So this is what we nowadays call L1 penalty. And so adding this L1 penalty is the main idea of shaping Lasso estimators. In general, the minimizer for the objective function, which is in the equation 1, finding this minimizer is basically the objective of a Lasso estimator. And in this talk, we are going to study this type of the problem, which is if somebody give me a vector y and also give me this model matrix x, so the x and y is a given, and how do I solve the minimization problem in the equation 1 such that I can get to the Lasso estimator. I'm not going to talk about the statistical properties of the Lasso estimator because this is already a huge literature in statistics. So today's talk is more about how to solve numerically the problem in the equation 1. So now we are going to consider how to solve this problem. So my background is in statistics, but I'm going to have to confess that this particular topic that I choose to talk about is probably heavily involved with computational mathematics and algorithmic analysis, as you will see. So our objective is to minimize this objective function, and what will be the difficulty of solving this problem. So first of all, there is no closed form solution for the aforementioned minimization problem. I probably will say that it is no closed form in the narrow sense. If you are willing to, for example, bring in the notation such as subgradient and things like that, you may still declare that there is a closed form, but here I'm excluding those possibilities, saying that you don't have this classical, the closed form solution in the classical sense. And so most of these algorithms, so the state-of-art algorithm to try to find the beta is through some iterative algorithms. And I'm going to call those Lasso algorithms, all those recursive algorithms will be called Lasso algorithms. And I use beta sup k, and k is the indicator of how many iterations it has already been taken. So obviously you want to, so this beta sup k is the case estimator of the beta, and you want it to converge to the beta star, which is the ground truth, as the k goes into infinity. And if we want to, it turns out that in this particular problem, we evaluate the performance of our estimator in the following way, and that is because of later on I may discuss that what will be the challenge if we want to solve the problem such that beta k converge to the beta star, because that by itself you may have to introduce some additional conditions, which is make the problem like less general, and we try not to do that because we still want to get a more general results in terms of the convergence. And in order to do that, we have to tailor all the criteria a little bit. So the exact criteria that we are going to adopt in this work is that, so recall that f is the function, and I'm going to assume that everybody can see the curves that I'm using on my slide. I use beta hat to indicating that the minimizer that can be achieved for this f function, and f beta k is how much you can achieve after case iteration. And if this difference, so f beta hat is the smallest possible you can achieve as the minimum value for the f function, and as long as it is within epsilon precision to the smallest it can achieve, then we declare that epsilon precision has been achieved. And in this talk, we are going to be using this as a criteria to evaluate the different algorithms. Now, so the objective for different iterative algorithms is to try to reach this epsilon precision. And how do we evaluate the efficiency of different algorithms before they can achieve the epsilon precision? We use this order of complexity idea, which is basically the numbers of numerical operations in order to achieve the epsilon precision. A lot of time, it also involves the form of constant times a polynomial of some parameters involved in the problem complexity, which I will specify later. So it may be up to the sample size, and it may up to the dimensionality of the data, which is p. Of course, it is also a function of epsilon, because epsilon precision is what we try to achieve. We don't use the total numbers of iterations because that is unreliable indicator. You can have less iterations, but within each iteration, it is a lot of computing has to be done. That does not lead to a fast algorithms. We don't use the running time because it heavily depends on your implementation. Is this a CPU or GPU? Is this a Python or R? All this will make difference in terms of the running time. So running time is not considered a reliable way to evaluate the efficiency of an algorithm. So, and eventually, we are going to talk about the following things that we can achieve. That is, we compare our method to 4 main ideas in turn towards solving the Lasso problem that we can find in the literature, and those are the state-of-art algorithms. As a matter of fact, in the next session, I'm going to review the state-of-art algorithms. So they are the, you don't need to remember them at this time. They are ISTA, FISTA, coordinate descent method, smooth Lasso. But this main table down here is a way to summarize the main contribution that I'm going to talk about. That is, we are able to develop a method such that if we consider the order of complexity that it is required in order to achieve the epsilon precision, if we use ISTA algorithm, the best you can do is to prove that the order of complexity is the big O of 1 over epsilon. And this big O basically means that the total numbers of numerical operations is a hidden constant time 1 over epsilon. So it's basically we sometimes if we simplify this, we simply say that the convergence rate is 1 over epsilon. Here, obviously, the convergence rate also depends on n, depends on p, but it turns out that those are the common factors. So we, to illustrate our improvement, so those are not included in this table. And for the FISTA, it turns out that you can prove a better rate. So this is 1 over square root of epsilon. So epsilon typically is a very small positive value. So 1 over epsilon is going to be bigger than 1 over square root of epsilon. And for the coordinate descent, it turns out that the best we can do is 1 over epsilon. Smooth Lasso is 1 over epsilon. So it turns out that all the existing methods that we can find in the literature, they are all seems to be the log polynomial of 1 over square root of epsilon. What we can do is that we can add a log in front of this 1 over epsilon, showing that using the homotopic method that we developed, that I'm going to talk about later, and we can actually bring down the order of complexity to the log polynomial instead of a polynomial of 1 over epsilon. And now, next, I probably, in terms of the, because of the time, I will quickly go over the state-of-art algorithms, which we use as a benchmark in our analysis. So the first one is called the ISTA algorithm. And I probably, I add a lot of technical details into my slides, but you know, nowadays, one thing I learned from the remote teaching is that the student can always rewind the tape, and because this talk is also recorded, so if you can always watch it later, and if there's anything that you don't have time to read it during this live presentation, you can always pause it and read the slides by yourself. So I'm going to not reading all the stuff that I'm talking about that I listed on my slide, and I'll simply say that there's something called iterative shrinkage threshold algorithms called ISTA, and Lasso, you can say that you can formulate as a special case of the ISTA, and then you can take advantage of the ISTA algorithm, which is basically you use a quadratic approximation at each local step. And then you minimize this surrogate function, which is a quadratic approximation of the objective function at that time to get your next estimate of the beta. And this method in general is called ISTA. It is an iterative algorithm. And this is a kind of algorithmic description of what the ISTA algorithm is. And in each step, it uses it solves a minimization problem, and it turns out that this minimization problem, by using the operator of a shrinkage, you can write this as this form, and implementing this form can be very easy. It's basically a matrix vector multiplication. So each iteration involving a matrix vector multiplication. So the total numbers of operations in each iteration, it can be big O of a p square. And according to this paper, the best rate you can show in order to show that how many iterations you will need in order to achieve epsilon precision is basically a constant over epsilon. And so because of that, then you can declare that the E-star algorithm, the order of complexity that is provable is 1 over epsilon if we can ignore this p square, which is kind of a common factor in all the algorithms that we are going to study. So because it's a common factor, so we probably can ignore them for the purpose of comparison. And another method is you can think of it as an improvement of the E-star algorithm is called FISTA. So the only thing which is different from E-star is that in the name, there's a fast in front of the E-star. And what it does is that it takes advantage of this idea of accelerated gradient descent method. And what it means is that it turns out that it is not only taking the immediate gradient. There's a way you can take advantage of the previous, the gradient in the previous step in order to make your algorithms converge faster. So AGD, accelerated gradient descent method, is a hot topic in the optimization, in the numerical design. So this method is kind of a improvement of the previous one by replacing the gradient descent with the accelerated gradient descent, taking advantage of the momentum. And so because of that, you can prove a relatively better rate. So here is the details of the FISTA algorithm, which is if you're looking into it, it is basically one way to realize the accelerated gradient descent idea to bring into this algorithm. And within each of this iteration, you can see that still the main difficulty in terms of numerical efforts is this matrix times a vector. So p square is still the numbers of operations. A constant times p square is roughly the numbers of numerical operations that is needed within each of this iteration. And because it is an accelerated gradient descent method, so you can actually prove a better rate, a better convergence rate before it can achieve the epsilon precision. And this is a constant over square root of epsilon. So overall, then you can prove a better convergence rate, which is simply speaking is 1 over square root of epsilon. And there are some other methods which you probably cannot improve the convergence rate, but it is very popular in terms of the statistical practice. So for example, the coordinate descent method, which means that you choose to update one entry at a time in your algorithm, and then you circle through all the coordinates. And for this method, you can write a simple updating form into it. Because there's only one coordinate involved in each time, so the particular step of updating can be very fast, but you have to cycle through all the coordinates. So overall complexity is not going to be low. And essentially, this is a gradient descent based method. So the convergence rate is not going to be that good. So here I listed the algorithmic description of the coordinate descent, and so if we're thinking about each cycle cycling through all the coordinates, then the total numbers of operations is still p square for each cycle, and you can show that the order of complexity is still something like 1 over epsilon. So overall, this is still a 1 over epsilon order of complexity algorithm. And some other improvement we notice is that there has been effort which is trying to replace the objective function so that we can achieve a fast algorithm, fast iterations. So for example, we have seen there's one paper which is talking about how to replace the original function with a smoother function so that you can overcome some of the difficulty that involved in solving the Lasso problem. But those algorithms, we found that along this line, the best we can find is this one by Mukherjee and his co-authors. but if we look at the order of complexity, it still seems to be 1 over epsilon. That is the best rate that can be achieved, can be proved for those type of algorithm. Now, after reviewing all these methods, this is what we believe are the state-of-art methods in terms of solving the Lasso problem. Here, I would like to bring back this table showing that what we try to achieve, all those existing algorithms, it seems like when I prove the order of complexity before they can achieve the epsilon precision, they all seems to be either 1 over epsilon or 1 over square root of epsilon. And the next thing, in all proposed algorithms, we're able to show that the number of complexity can be bring down to log of 1 over epsilon. And here is the idea of our proposed method, which is also called the Homotopic method. So the motivation behind our development is that from the optimization literature or the numerical mathematics, we kind of know that there is a scenario where you can have a fast convergence. So for example, if you have a quadratic function, then then one step of Newton algorithm give you the final answer. So it only take 1 iteration. So that's an ideal case. And but in general, if you have some strongly convex objective function, and in particular, the objective function is well conditioned at the minimum point, then you can prove 5 convergence rate. This is kind of the rule of thumb that we try to that we try to take advantage of. So we know that in this situation, if we have a strongly convex and well-conditioned objective function, then there is a provable fast rate for algorithm, and it could be accelerated gradient descent algorithms and so on. But the challenge associated with the Lasso function is that it has an absolute value function, which is embedded in this L1 norm definition. Recall that the L1 norm of a vector is the sum of absolute value of its entry. And this absolute value function creates a problem because at the origin, it does not even have a derivative. So it's not a smooth function. So, and then this motivates us to consider the following, which is how about so recall that if it is the Lasso problem, then the objective function, the first term is just like this one, which is the residual sum of the square, and the second term is lambda times the L1 norm, which is the sum of absolute value function. But we know that the absolute value function is the one which generates the problem. So we want to replace it by something which is potentially strongly convex and also well conditioned, so that we can declare that we can have a fast convergence rate. But of course, we still want to solve the original Lasso problem, because Lasso problem has so many provable, nice statistical properties. So we don't want to deviate from that. We want to still find estimator, which is a Lasso estimator. So because of that, I want my function converge to the objective function, which is the objective function of the Lasso estimator. And the trick is that I'm going to use a hyperparameter t to control. So it's a sequence of a surrogate function, which is called f sub t. And as the t goes to 0, it converges to the absolute value function. And for each fixed t, when t is bigger than 0, for this fixed t, f sub t is a strongly convex and well-conditioned function. So for each fixed t, it is a strongly convex and well conditions, because I need these 2 properties so that I can obtain a better convergence rate. And the homotopic method is that, recall that the main idea is that we have a sequence of a surrogate function, which is called f sub t, and as t converges to 0, eventually it converges to the absolute value function, the L1 norm in the Lasso estimator problem. And at each step, we minimize with respect to f sub t, the surrogate function, instead of the original objective function in the Lasso estimator. So here is the idea of homotopy. We carefully design a sequence of this t parameter, start from an initial value, which is t null, and then we gradually reduce the value of the t. So it's a sequence of value that we pick for this t, and within for each of this fixed value t, we minimize this objective function. But this objective function, the L1 part, is replaced by the surrogate function, which is this f sub t, with respect to the element in this decreasing sequence. And this sequence decreased, monotonically decreased to 0. And when we consider minimizing this this objective function, we use some accelerated gradient descent method. And at least the advantage is, at least in theory, we can obtain a better rate of convergence. And we take advantage of the strong convexity and well-conditionedness of this objective function. And of course, we are going to solve this iteratively, so which means that within each sub-problem, we are not going to let the algorithm run until it converges. We actually let it run when certain precision is reached, but this precision is not necessarily the global epsilon precision we want to achieve. It's kind of a precision designed locally for each of this objective function, and then you stop that algorithm, and then you start working on the next surrogate function. Next, try to minimize the next objective function. So it's kind of solving a sequence of minimization problem, but for each of this optimization problem, you only run a few steps of accelerated gradient descent method. And in your algorithm design, you kind of design how many steps you run. You let the accelerated gradient descent algorithm run, and you always take the previous stopping position of stopping position of the previous subproblem as the initial point of the next next subproblem, and keep on doing until you achieve the desirable precision in the solution. So this is this method is what we call the homotopic method. So the main idea is we solve a sequence of optimization problem, and each one have a surrogate. Replace the objective in the Lasso problem with a surrogate function, and we solve it sequentially with carefully designed stopping rule within each iteration. And overall, we can prove that this method can give us a better convergence rate. So this is a formal description of this iterative algorithm. So you have an input, output, and you have a hyperparameter to control the homotopic path, which is define the subproblems you want to solve in each iteration. And within each iteration, you use you run a few AGD, accelerated gradient descent steps, to try to minimize the current objective function, and then stop and then start working on the next objective function. So this is the idea of a homotopic method. And there's several challenges that we need to overcome in order to realize this idea. The first challenge we need to overcome is that how to define this surrogate function. So this surrogate function, needs to have some properties. So this is kind of the work of a reverse engineer, which is we kind of know that we want to design a surrogate function such that we can prove a faster convergence rate. Then we have to list all the conditions we are going to need in order to prove those convergence rate. And so this kind of give us the properties of those of the surrogate functions that we need to design. So for example, you need to converge to the absolute value function. In particular, we want the when it's close to 0, it's a quadratic function, and when it's far away from the 0, it does not have to be a quadratic function. And overall, this function must have a continuous. It has to be continuous differentiable, and so on. So we listed a few conditions that this surrogate functions needs to be satisfied, and after some work, this is the surrogate function that we found that can satisfy those conditions that we listed earlier. So as you can see that this is a function. This surrogate function is controlled by the hyperparameter t, and x is the input variable. If x absolute value is less than t, it's a quadratic function, and if it's outside t, it is absolute value function of x. But the coefficients in front of the absolute value function needs to be designed in this way, and it also have some additional terms, and these additional terms include a part, including one of them, which is 1 over absolute value of x. And the purpose of the reason behind defining such a surrogate function is that it turns out that a surrogate function like this will satisfy, will provide us the properties that we need in order to derive faster convergence algorithms. So this is going to be, you can prove that this is a strongly convex for fixed t bigger than 0. This is strongly convex, and it is well conditioned, which is another critical conditions in order to obtain a fast algorithm. Then once we have the above surrogate function, then the objective function at each time is going to have this form. Notice that the second term is replaced by the function which is defined above. And in terms of illustration, this is what the function looks like. The first row, t is recall t is a hyperparameter controlling the surrogate function. So t goes from 1, and then next is 0.1, and this is 0.01. And the solid line always is what does the function f sub t looks like, and the dashed one is the absolute value function. So you see that absolute value function is not does not have a derivative at the origin, and this is where the difficulty comes from, because of this you cannot prove some nice numerical. It's hard to derive nice numerical algorithms to solve this, to minimize this type of the function, and we need a well-conditioned, smooth, strongly convex function in order to do so. And this is when t is equal to 1, this is what the surrogate function looks like. And when t is equal to 0.1, recall that if t decrease to 0, the function converge to absolute value function. So you see that it becomes closer to the absolute value function, and t is equal to 0.01, then it almost coincide with the absolute value function, even though mathematically they are still different. And the second row is kind of the first derivative. So if it's absolute value function, the first derivative doesn't exist at the origin. So that's why you see there's a jump point. The dash is corresponding to the absolute value function, and you see that there's a jump point at the origin. But those are solid curve representing the first derivative of the surrogate function, which is the f sub t, and it becomes closer and closer to the to this stepwise function, which is the first derivative of the absolute value function. And this is the last row is the second derivative, and you can see that the second derivative, the main idea is at a neighborhood at origin, it is flat, and this is a way. This is a way to define such that it provides the well-conditionedness in the objective function everywhere globally, so that we can prove a better convergence rate. But as the t converges to 0, this plateau kind of shrinked. Eventually, it shrinks down to 0. That means that it converged to the absolute value function. So now, this is overall description. If I put all those pieces together, this is kind of the comprehensive way to describe the algorithm that we talk about. It's a homotopic approach. You divide the original minimization problem into a sequence of minimization problems with different objective, and within each iteration, you kind of control the numbers of steps, numbers of iterations. You let the accelerated gradient descent algorithm run, and so this is a kind of a formal description of the entire algorithm. So I'm going to, for the interest of time, I'm going to skip the detailed description of this part, and there's some additional explanation on the notation that is used on the previous slides. I listed here because this is a recorded talk. You can always pause and go back, and if you have any question on the previous slides, you probably can look at these particular slides. choosing the initial point is also a technical issues that we need to solve. And we found that in order to prove what we want to prove, we need to carefully choose the initial value for the t, and it turns out that if we choose the t that satisfies this condition that is described in this lemma, then we will be able to prove a better upper bound that I mentioned earlier. And some other details is that the t is a value of the t, which is a hyperparameter, is shrinked by constant factor each time. And another thing is that in the inner loop, it turns out that you need to control the numbers in order to achieve a better convergence rate globally, you need to control the numbers of steps, the accelerated gradient descent steps in each within each subproblem. And it turns out that if you choose this epsilon defining this way, we can show that globally we can achieve a better convergence rate. So with all these components putting together, we derived the algorithm, and in particular for this derived algorithm, we can establish the following results, which is, first of all, in the inner iteration, if I specify this inner iteration, which is, as I talked about before, then if I want to achieve this precision within each subproblem, then the total numbers of iterations that will be needed is something which is a log of 1 over epsilon. This is probably not surprising because before I start, I know that I want to take advantage of the optimal convergence rate that is provable by using accelerated gradient descent. I also know that if I can successfully define a objective function which is well conditioned and strongly convex, then this is provable. And the hardest part is to find a surrogate function such that it does have all these properties. But once you find those surrogate functions that does have all those properties, then I will use the method in the existing literature to prove that the total numbers of iterations that it will be needed in order to achieve this precision is log of 1 over epsilon, which is kind of a no in the optimization literature. The second thing is I also need to figure out how many outer iterations it may need. Recall that that means that how many subproblems I need to solve, and each subproblem will change the objective function with a different surrogate function. So how many outer iterations I will need in order to achieve the global epsilon precision. And it turns out that I can also show that the numbers of iterations is something like a log of 1 over epsilon. Here, obviously, I skipped a lot of technical details, which is the part that is necessary in order to establish a rigorous mathematical statement. But with all of that, the overall result is that if I want to achieve the epsilon precision, then for the outer iterations, the total numbers of steps can be controlled by log of 1 over epsilon. And moreover, if I combine the previous two results, and it's not like a multiplication, it's actually, it's a summation of numbers of steps in each subproblem. But for each subproblem, it's not a constant, so you cannot simply multiply the previous two. But nevertheless, we can still figure out the mathematical details showing that the total numbers of numerical operations in order to achieve the epsilon precision is this log of is this square of log of 1 over epsilon. And you can argue, I hope that it is obvious that the log of 1 over epsilon is much smaller than 1 over epsilon. Okay, so we have some discussions. We didn't solve the Lasso problem directly. Recall that the Lasso problem is to uncover the true value of the beta, which is the beta star that we mentioned at the beginning of the presentation. So we didn't exactly prove that, we didn't do the things like what the people typically do in statistics to prove the minimax rate of convergence for our beta estimator. But here we argue that there are two observations. First of all, when we have for the solution we get, if we use this inference error as the criteria, then we can show that they are basically, if t goes to 0, then this difference of the two results basically converge to 0. And that is, so if we only care about the prediction error, then the result that is obtained by a homotopic method is going to be comparable to the one that you solve the original Lasso problem. But remember that in solving the original Lasso problem, you may not have a provable fast algorithm to do that. And the second part is if we really still are very keen about the exact support recovery, we found that for that end, you have to assume a lot of things about the model matrix. So we made some discussions in our manuscript, but I probably should stay away from the details or discussion on when this is achievable. And we also did some numerical experiments. So I probably, it looks like I have 5 minutes left. I'll quickly go over the numerical experiments that we did. We follow some classical way of doing this experiment, which is we generate the Gaussian distributed predictors, and those Gaussian distribution have they are standardized. So in terms of the covariance matrix, all the diagonal entries are equal to 1, and all the off-diagonal entries equal to rho. And this rho, it turns out that after some experiment, we decide to choose this rho to be 0.5. And so that gives us a way to generate the predictor vector, which is x. And for the beta, we use this exponential function to generate the beta. So beta, each of this beta is kind of an exponentially decayed function with respect to index I, and then we see that how if we can, the z is the y noise vector, and we study if we use our method or we use other methods, how many numbers of how many numbers of numerical operations it may need in order to achieve the epsilon precision. So this table, we listed E-star, FISTA, and our methods. And probably instead of looking at this table, it is more clear to look at this two figure. So this figure, we have 50 observations with 20-dimensional data, and this is 50 observation with 80-dimensional data. So this circle decorated is the E-star algorithm. So the horizontal axis is log of 1 over epsilon, and the vertical one is the log of numbers of numerical operations that your algorithm need in order to achieve this epsilon precision. And of course, the lower this curve is, the better the algorithm is. And for the asteroid decorated curve, this is increase of the numbers of log of the numbers of operations for the FISTA method. Recall that E-star, the provable order of complexity is 1 over epsilon, and for the FISTA is 1 over square root of epsilon. And for all method, and the provable upper bound is log of 1 over epsilon, but here we further take a log of the numbers of numerical operations. So then in theory, this curve is supposed to be log of log. So that's why you see it is so flat. And in another case, you can see the similar things. This is the highest curve is corresponding to the E-star algorithm. The middle one is the FISTA, and the lowest one is the all method. So empirically, we can also observe that our method converge faster than other method. We did another experiment, and in this experiment, so we changed the setting a little bit so that more coefficients, so the coefficients become even sparse, and we kind of see that same pattern appear, which is if we use our algorithm, so we need less numbers of numerical operations in order to achieve the same precision. So I want to, before I conclude, have two more slides. So this slide, I will just briefly mention that another popular idea in solving the Lasso problem is to use the path following, is to develop a path following algorithm, which is the main idea is that you initiate with a big lambda, and then realizing that the solution beta is essentially a function of a lambda, and it's a piecewise linear function. So what you need to do is to identify those change points, identify those intervals for those piecewise polynomial function, and then corresponding there's a faster solution. Because by knowing that the solution path is piecewise linear with finite change points, then you can develop a fast algorithm accordingly. So a closer related topic is the path following algorithm, but it turns out that many people believe that path following algorithm can solve all the Lasso problem, but the reality is that it is not true. If you closely examine those path following algorithms, they all require some very strict conditions in order to make the path following approach work. And as a matter of fact, we actually come up with, in our discussion, we come up with a counterexample showing that you can almost, in general, if you define a path following approach, you can always find a counterexample showing that that algorithm, its condition will be violated for it to work. So in summary, I talked about a newly designed homotopic approach that can solve the Lasso type of the problem with better theoretical guarantee. And I think we started this project because of the interplay of statistics and computing. Statistical problem essentially become a minimization problem, which is a computing problem we need to solve. And once we start thinking about what will be the best strategy to solve this problem, we we run into this idea of homotopic methods. But on the other hand, after finishing this project, when we look back, we also found that a lot of statistical literature seems to be restricted to making strong assumptions in their algorithm design in order to make their method work. But it seems like this homotopic approach you don't have to make those strong conditions in order to make your method work. So I think it is a promising direction to. It's a potential good way to. A good tool to use to look at, to revisit some of the existing literatures in statistics. And we have an archive paper if you are interested in the details of what I talk about today. And finally, if you want to know more, here is my contact information. And finally, I want to thank you all for being here today, for taking your time to listen to my talk. And I'll stop here. And I'll be happy to take any question.
Thank you for your talk.
Thank you very much. It's a very nice talk. May I ask a question? I think that your beta tilde will convert to beta heads, both in prediction known and L2 known converge to 0. Do we have convergence rate for that? Because we know that under some regularity conditions, we know that the L1, L2 prediction known of Lasso estimators converge to its beta star at a certain rate. And that rate actually is important in many methods and many theories.
In this, we kind of solve a different problem than the one that is traditionally like the minimax rate literature in the statistics. Here we kind of using the epsilon precision and the order of complexity in order to achieve the epsilon precision in the minimization problem. We did not work on the other part, which is kind of characterizing the other part of the other type of the convergence rate, like the minimax rate is the estimation rate, because it's kind of another to me, it's kind of another paradigm to formulate the problem. The mathematical details will be very different. The objective, the criteria function seems to be very different. But I think we kind of this is a more emphasis on the numerical convergence instead of the statistical property of the Lasso method. The statistical property of the Lasso method is a kind of a well-studied subject by now.
Right. I mean, because at the beta hat, usually we do not actually accessible to us because of the minimization problem. So we have to use some kind of algorithm like your algorithm. So eventually we obtain the beta tilde. But when we're doing many analysis and many theoretical develop, we just assume that the beta hat is available to us. And we just directly use that convergence rate.
Right.
Yeah, but I think probably more correct way is to use the convergence rate of beta tilde. So,
oh, I see.
So that beta tilde and the beta hat is actually smaller than, for example, the estimate rate of Lasso. So,
right. Yeah. Well, that's a very good question. Sorry, I probably misinterpreted your question before. I don't have an offhand solution to that, but I think somebody, but you probably know that if you read the statistical literature, most people seems to assume that the minimization problem can be solved perfectly, and then you can get a minimax estimator. But beta, if you have a beta tilde close to beta hat, or you get approximate Lasso estimator, what can you say about it? I'm not sure that I have seen many results on that regard. At least in the statistical literature, I don't think, maybe you know some papers, but I'm not aware much work in that direction.
Okay, thank you. Yeah.
And I guess it probably also depends on how do you quantify the beta tilde, because beta tilde may depend on many things, like how many numerical operations you allowed, or do you use how many iterations. It probably highly depends on the algorithm that is adopted, and that's probably why it's hard to say something general.
Okay, yeah, thanks.
So it's a very nice talk. I think I want to understand. So the R1 norm is basically the main feature is the sparsity. I guess in this problem is the same, like image processing people typically use. When you use a sequence to approximate that, to what extent you affect the sparsity feature?
Oh, that's an excellent question. It's a very fundamental, and I think there's a part of the story. What I said in the paper, we kind of described the whole story, but in the past 50 minutes, what I said is not 100% of the story that I would say due to the time limit. I think as a matter of fact, if you're not using R1, the absolute value function, we can argue that then you basically cannot achieve the sparse estimation case, because only the R1 norm, you have to be discontinuous at the origin in order to doing this like soft thresholding. The other smooth function cannot achieve that. So in this sense, all these surrogate function, the point is you should not let the t go round down to 0. I think the more better, more scientific story is that you let the t run when it is small enough, the epsilon is small enough, and then you change to some Lasso algorithms. It's kind of bring you down to pretty close to where your solution is going to be, at least in the sense of the inference error. But then if you cannot continue using this globally smooth function, because then you cannot achieve the sparsity.
I think that some people use the RP norm, let it just p close to 1. That's in the image processing literature. That's another way they want to to modify the quality functional, here let the trade-off functional, also to keep some sparsity, I think. Yeah. Anyway,
yeah, I think
okay.
we are kind of try to replace the L1 norm, knowing that it has a certain disadvantage of it's a challenge to working on it, but we kind of lay out what do we want to achieve at the beginning, like those. We realize that the surrogate function needs to be strongly convex and well conditioned, so we design our surrogate function in that direction. But those LP, we also know that there's a lot of literature talking about replacement of the L1 function. Like LP is a one, P is greater than one is a one possibility. But that kind of it's doing without a well-defined purpose. It seems like.
You're right.
Right? Because right.
Yeah.
I mean, okay, I do it, but then what do I want to achieve? Can I achieve a better rate, or what are the things I can declare afterwards?
Okay, thank you. Yeah, nice.
Okay, thanks, Xiaoming, for excellent talk and very interesting discussions. I think Haridash has to leave earlier because he has a meeting, but he wants me to thank you on behalf of our TADS for giving this excellent talk.
Thank you, Lily, and very nice to see you and see all of you.
Okay, all right.
So
thank you.
Is this talk the only thing? Is there any time that Xiaoming will have some time with us, or?
Yeah, I can stay. I can stay. I guess until 2:30 my time, which probably